Good morning.
Very good morning.
Good morning. This is Mr. Henry Clement for your Year 9 Science. Today we are talking about rate of reaction. This is the book we are going to follow. Okay. Measuring the rate of reaction. The rate at which the reaction takes place can be measured by working out how much of one of the products be made in a given time or how much of a reactant is used up in the given time. This is a process. Okay. If you are using to make a cake, you have some flour. And then this flour will allow you to make cakes. So if the flour have been used fast, it also means that the cake also making quite fast, right? So if there you can see a lot of cakes have been made, so you can know that the rate is also fast because many of the flour have been used. Okay, this is the meaning of this sentence. Okay, so for a process, you can always measure the product and also the reactant. For example, if your product has gas here, okay, so for example, the reaction you may look at is if the product here you have the CO2, which is a gas, then gas is easy to collect and measure. So you may use a syringe. Okay. Okay, this is the example of that. Okay. We all know that when you have marble cheese and acid, this is a carbonate. Okay. So acid and carbonate will produce a lot of gas. Okay. So if you're using a syringe, the gas will produce and create some pressure and push the syringe, and you can do the scale here. This is the example of the real examination, the experiment. So there's one thing here. If you have magnesium and hydrochloric acid, magnesium and hydrochloric acid, this is the magnesium and HCl. All you get here will be MgCl2, this is 2, plus a H2. So There are two products here. This is in aqueous, which is dissolved in water, and this is a gas which is coming out. So to this side, okay, if you want to measure the MgCl produced in the solution, it's very hard. How can you know that? Okay, but it's easier for you to just measure the gas. Okay. So again, you must know that every time when we talk about the rate, this is a volume of gas produced in a particular length of time. You need to compare it with the time. Okay. To collect the gas, you can attach a syringe to the top of the flask so that no hydrogen can escape. You can also use scales on the syringe to measure the volume gas produced at different times during the reaction. The table below shows that how to attempt this apparatus. Okay, at the time 0 when we start, the volume produced is 0. After 10 seconds, okay, after 10 seconds, it will be 10, 30 seconds is 10, 60 seconds is 20, okay? And then once you plot the graph, can you see? After some time, this is every time is 10. After 60, it will become 6. And this is something which is 6, okay? And then again, 40, 48, and then I'm up to here, you can see 66, it doesn't move anymore, okay? So when you plot the graph, it should be like that. It's a graph, okay? Okay, if you are plotting it correctly, it should be a smooth curve, right? This one is the 26 is out of the line. Okay, no worry. Sometimes you call this is anomalous. Anomalous. Again, in our mathematics, we know that this is the continuous data. Continuous data. It's not the discrete data. Discrete data is something that you cannot have an intermediate. You cannot join the line one. Okay. Change in the rate of a reaction. Okay. When you try to do some reaction, sometimes your reaction is fast, sometimes your reaction is slow, right? Okay. So measuring the rate of reaction by finding out the loss of mass. Okay, if you don't want to collect the string, just now I showed you this one, you can see that actually this magnesium, okay, and this hydrochloric acid, you can see that the gas is bubble off, okay, so that the weight will be lighter, okay, just like this. If you measure the rate of reaction, you can find the rate changes as the reaction proceeds. For example, in the reaction between the calcium carbonate and hydrochloric acid, loss of bubble of carbon dioxide are given off at the start of the reaction. As the reaction continues, fewer and fewer bubbles are produced. This reaction has been slowed down. Okay, now we need to show the graph. Okay. This one we also can use this graph to show that investigate into the rate of reaction between the calcium carbonate and the okay mass of the carbon dioxide produced. Initially is they increase very fast, and then the reaction slowing down, and then eventually they stop. The reaction is complete. No more product is being formed. So we call it, this is a steep. This is less steep. This is no reaction. Level out. Level out. Other type of the measuring will be like when you try to measure the calcium carbonate. This is a filter funnel, and then you can measure the cylinder using cylinder upside down it. Then you can see the gas bubble off. Then you can calculate by time as well. But the main important thing is that you need to compare to the time. Okay. Why does the rate of reaction change? Okay, now we need to know some particle theories. So particle theory, we have the surface area, temperature, and concentration. Okay. We have 3+1. The last one is the catalyzer. Okay, always have a 3+1. Remember this word. Okay. Why does the rate of reaction change? We can use the idea of the particle theory you have learned in stage 7 and 8 to answer this question. Okay, let me read to you this paragraph. For a chemical reaction to take place, the particle of the reactant involved have to collide with each other with enough energy to react together. At the start of the reaction, there are loss of particle. Yes, at the start of the reaction, there are loss of particle that have not reacted. Okay, collision happens frequently. This means that a lot of carbon dioxide is formed in the first 30-second period. As the particle reacts, okay, the number that have not reacted gets lower and lower. So that means that the remainder particle is just lower and lower already, the amount of them. The chance of the two unreacted particles collide with each other decrease. So if it's very hard to find the two particles that are still not reacted already. Which means that less carbon dioxide is formed, and the later 30-second period, it means that the rate of reaction is slower. Eventually, all the particles have reacted, there is no more collision that result in the production of carbon dioxide gas, so the reaction has finished. Okay, so we have learned 3+1. Remember, particle theory only have 3, which is the surface area, which is temperature, and which is concentration. Okay, this is related to the particle theory. And +1, which is not a particle theory, which we call it the catalyze. Okay, come. We should come back to the surface area first. When you have burned calcium ribbon in the Benson frame, it reacts very quickly with a white frame. If you place a larger piece of magnesium in the Benson, it does not burn. If you place a magnesium powder, it can be burned faster than the ribbon. Why does this happen? Okay. This is because the surface area. Okay, let me do some calculation for you so that you can understand this one. The rest you can read. I think your school also will be teach. If you need help, explanation, let me know. Okay. So, for example, if I give you a 9 times 9, this is a cube 9, 3 times 3 times 3. So the surface area of this one, okay, the volume is the same lah, okay. So this is 9 times 6, 9 times 6, you get 54 unit of the area. But if I take out one by one, this is 1 times 6, so each one is a 6, the surface area. But altogether, I have 9 times 3, 27 pieces. So I have the 162, right? So the area is 3 times as compared to this, can you see? So if I can able to cut this one even smaller, the area will become increased. Just like this, only a very big cube, you know? It's already 3 times of the surface area. So the surface area here is larger. It means that when I open down, the place you can react is only 54. It's this size. But the 162 will be like maybe 3 times on this side. Can you see? The surface area to be that you can react compared to this one and this one is that you have the more surface area here. So this is another example of calculation. So it means that, for example, if you are making a chocolate malt, chocolate drinks, okay? So if you're using this is hot milk, If you're using the very big cube of chocolate inside, you would need to stir it long time. But if you get this is hot milk, you get a thinner one, okay? So I think you can stir it faster. If I give you the powdered, I think you can just stir it within a second. It's very fast. Okay, so this is the very first thing about the surface area and the reaction. So the largest one will be like maybe a cube, a block, the larger one, and then you have the ribbon, and then we may have the powder. The next one, okay. Just now beside the, can you see this is the forming of the, okay, this one you can see the forming of the precipitation. It means that if the hydrochloric acid and the sodium thiosulfate react together, sulfur is formed. The sulfur make the cloudy. It means that the crystal clear water has become like some particles is there. Okay, some precipitate is there, so that initially you can see the cross, which is the through the grass, but now it's become blur, and then at the end, actually you cannot see the cross anymore. It means that they're covered already. Okay, let's see. If we're going to investigate how temperature affect the rate of reaction between the hydrochloric acid and the salt called sodium thiosulfate, the reaction is a good one to you because that is an especially easy way to measure its rate. If you mix the hydrochloric acid into the solution of the sodium thiosulfate, the mixture becomes cloudy. This is because the sulfur is produced. Sulfur is insoluble in water. Insoluble, we call it a precipitate. We can time how long it takes for enough sulfur to form to make it impossible to see through the liquid. So again, let's using the chocolate drinks. Okay. I think you have ever made the chocolate malt drinks. Okay, today let's use a powder one. Okay. Or at night later you can try to do it. To get your own experiment. Okay. Using the same amount of water, to be fair, but this is the hot water. This is the room temperature. This is the cold water, maybe about cold water, which is the water with ice. With ice. Okay. So you put in the 3 spoonfuls of the same amount of the chocolate powder, and then you try to stir it. The hot one can be done within seconds. The room temperature may take about 30 seconds, and the cold one may take you about 5 minutes, 300 seconds. Okay, so the hotter the water, the environment, the reaction is faster. Right? Just like this, the powder is faster, this is slower. Last one, okay, no, this is a graph. Okay, for example, okay, how to read this graph? Okay, the amount of the reactant is the same. Okay, so the final stage, the highest volume you can gather is the same. But can you see this 41 can reach the maximum faster than the 30. 30 take a long time. Because just now the chocolate drink we have mixed the same amount of water and same amount of the powder. Okay, so the taste, the concentration of the drink is the same, but it's just you can mix it faster or slower. Okay, that's another way to describe. Okay, to describe the temperature's effect. Okay, if you have slower energy, okay, they are moved slower. So the successful collision is also less. So when you have moves faster, okay, the moment the time they meet to the frequency they can collide to each other is faster, and then with higher energy also the successful collision will be more. Okay, come last two. Concentration and the rate of reaction. If you carried out an experiment with the marble cheese and hydrochloric acid using the same size and same mass of the chips, the same temperature, so we control this one, the same size and same amount of the chips and same temperature, maybe the same shape of the beakers of flask, okay? But different concentration of acid, what would you expect to happen? Let's see. The result will be like the higher concentration will reach the maximum faster than the lower concentration of acid. Here is a graph of some typical result of the rate of reaction between the marble chips and hydrochloric acid. In this experiment, the volume of carbon dioxide have been measured every 10 seconds. If you see the graph that you do not get any more of the product, the carbon dioxide stop there. At higher concentration, you can get the same volume of gas, but more quickly. Okay, what does it happen? Why? Explaining the effect of the concentration. It is because, again, we can use particle theory to help you to explain this. This is a hydrochloric acid particle. The more concentrate means that you have more particles. This one less concentrated, like that one, it has less particle. So if you have less water, you want to get this one, I think only one do a work at a time, but this one maybe two, maybe three. So to react with these marble chips, the more concentrated, just like the more water, so they can react faster. This is less one. Okay, so each one will get combined with a particle. So if this one immediately get the purple color away, and then this to combine to become a new things. Okay, so this one is a less. the chances and the collision is less. So as the concentration is increased, the rate also increase. You can see, because more particle given in the volume, they are likely to collide more in the certain given time. Okay, just like I said, there's a 3+1, 3 particle theory, which is the surface area, temperature, and the concentration. Now we have an extra one. This is not particle theories, but this is so-called the catalyze. Okay. So can you see here? If you want to speed up the reaction, you can always increase the temperature, the concentration, and the surface area. But manufacturers have to balance the cost. Again, the increase of the speed of the reaction. Increasing the temperature can be expensive because energy costs are high. Increasing the concentration can also be expensive. Increasing the surface area may have a process to crushing the solid, which is could add a cost. So they are trying to do something, which is using the catalyze. Catalyze is something that will help the process to be faster, but it itself will not be used up. Okay, it's not a reactant, it's just a helper. Okay. Here, the manganese oxide. Okay, bubble of the are given off and break down slowly. Okay, if this is hydrogen peroxide, so you change to the water and oxygen slowly. But if you add the manganese oxide, so the reaction will be happen faster. You can see a lot of bubble. Other thing will be the law lever also can be doing. This is also catalyzed for that. The manganese dioxide make the reaction happen faster than if the hydrogen peroxide was just left it on its own. But at the end of the reaction, the manganese dioxide was still there. A substance that speed up the reaction but remain unchanged at the end of the reaction is called catalyze. Catalyze is often used to speed up reaction in the industrial process. The same catalyze can be used over and over again. This is usually much cheaper than the increasing temperature, increasing the surface area, and increasing the concentration. So in biology, the catalysts are called enzyme. So enzyme is so-called the biological catalyst. Enzyme helps to speed up most of the reaction that happens in your body. For example, enzyme are used to speed up the breakdown of the molecule of food in your digestive system so that you can absorb the small molecule into your blood. Hydrogen peroxide is formed as a waste product in many reactions in the cell of plant and animals. It is poisonous, and if it is not broken down into the harmless water and oxygen quickly, it will kill the living cell. All living cells have an enzyme called catalase, ASE, which is speed up the breakdown of the hydrogen peroxide. That is why all the fruit, vegetable, and meat you add into your experiment broke down the hydrogen peroxide very quickly. You can try, Some washing powder contain enzymes. They are called biological washing powder. They help to break down the stains such as food and blood. Okay, so this is today's lesson. Today we need to learn about measuring the reaction, which is we can measure on the reactant side of how the mass is lost, or you can measure on the product side how the gas is produced or how fast the precipitate cover the cross sign. Okay, and then we need to learn about the graph, and if this is steeper, means that the reaction is fast. If not steep enough, then it's called slowing down, and when it stops, there's no reaction at all. So when we talk about particle theory, we know that surface area, the more surface, the more you can react to. So the smaller size of the particle will give you a larger, higher surface area. So the temperature also has the effect on that. Okay, just like I show you the chocolate drinks. On the other hand, the concentration also affect the reaction. Okay, because the more you have the particles, they have a chance to collide more. Okay, lastly is a catalyze. Okay, catalyze is a thing that never use out by itself after the process, so it will be much more cheaper. Okay, that's all for today. I hope that you enjoy this short and brief discussion. I hope that later you can join me for the math class. Thank you very much. Bye.